next presentation comes from Manuel Ballesteros from CSCS.
Hello, everybody. My name is Manuel, and I'm here to present a work on behalf of the Working Structure Group of BSEF, which is something we have been working the last year or so. And then let's see how it goes. So first of all, I would like to introduce the new system that we are developing. It's called Alps. So the goal of Alps is to provide high-level performance to the Swiss world-class Switzerland science community. And during this journey, we decided to take a few naive, risky steps. Okay, we still want to provide HPC systems, but with a twitch. And some of the things are multi-tenancy. And when I talk about multi-tenancy, I want to be a little bit precise, because normally in this type of talks, when we talk about multi-tenancy, we refer to multi-tenancy from the workload manager perspective. And in this case, we are trying to shift a little bit this paradigm and move it into the infrastructure. So what does it mean? So what it means is normally, this is a term that is heavily used on, let's say, cloud providers, etc. In our case, as of today, we don't run virtualization for the multi-tenancy. And so we don't virtualize CPU, we don't virtualize memory. So what we do is we take a chunk of nodes, and then we isolated them from the network perspective, and then we give them to our users or partners or whoever you want to call it, for them to have some sort of freedom in order to shape the system the way they feel like. And another thing is we want Alps to be geographically distributed. Traditionally, HPC systems, you normally have one system, you deploy, you run it. In our case, we want to have multiple ones in case one site has a problem, we could replicate the configuration of the cluster to somewhere else. Okay, so this talk is most around system management. By system management, I mean the management plane that normally it ships with the HPC system in order to help you to make it running. What it means is operations like, for example, building images, how to deploy those images to the compute nodes, etc. So traditionally in HPC, when we talk about this topic, we have a very tightly coupled system. Some people will refer it as a monolithic system. And it has a lack of interfaces. That's not true. I'm just talking very roughly in general. But most likely the users will, either sysadmin or end users, will have some sort of a CLI, which will be the most common interface for them. Again, you can find workload managers with REST APIs today, but generally, traditionally, the CLI was the go-to tool to interact with HPC systems. And HPC systems are also known to be reliable and efficient. Again, some sites are more reliable than others, but thinking that they are not flexible in the way that they do a specific set of tasks, and those tasks are very well defined. So this approach tends to give you reliability. Now, in Alps, we use the system we are working with is based on a solution from HPE. It's called HPE Cray EX machine. And normally, when you will buy this appliance, they will offer you two types of solutions. One is called HPCM, and the other one is CSM. In our case, in Alps, we use CSM, which is the more naive approach. HPCM is more HPC traditional way of thinking. CSM is a little bit more bold approach, I would say. In this case, the management place is composed by the set of microservices which are orchestrated by a Kubernetes cluster. And within those microservices that do different things, I highlighted here where do I have the most common ones. For example, you have the one called HSM, which will define what a cluster means, and a cluster in this case is a group of compute nodes. With HSM, you can also do hardware inventory, so you can query based on compute nodes which hardware are there, which type, etc. Then you have the CFS, which is the configuration framework system, if I remember correctly. And with this service, you will do things like creating configurations, creating recipes based on scripts that will ship within CSM, and with them you could do things like building images or link them to specific compute nodes to do further configuration, like for example networking, file systems, etc., installing packages, etc. Then we have IMS. IMS is the service to you can also build images with IMS in a different way, but most likely you will use it for image inventory. Okay, so the images are stored on a S3 bucket, and you will use this microservice in order to manage it, download images, push it, make it available to the compute nodes during booting, etc. The last one is the boot orchestration service, and the service is in charge of deciding which kernel parameters are sent to the Linux kernel when it boots, which configuration is going to finish the configuration of the machine after booting, which image is the one that the node is going to boot with, etc. And the last one is the CapMC, basically just power management. You shut down machines, you power on, you reset it, etc. And then there, okay. And here you can see, based on a high-level overview of the different layers that we could say a HPC system have, which services are responsible with. Now, I already mentioned briefly about this. So this is just a diagram of how high-level overview of how things looks internally. So you are a user, a system administration of the system, and you will create your Ansible scripts. This is the base, not the only one, but the most common one in order to create your recipes. You will ship it into a Git repository, which is then replicated to another Git repository, which is internal to the system. And from there, you just talk to CFS in order to in this case, to build an image. And again, this is based on Kubernetes. It will spawn a pod with a few containers. One is going to have the base image, your baseline, and the other one is going to be running Ansible, which will SSH to the other container and then do the changes it needs. Once it's finished, the target image container will have the final root file system for the nodes to boot, and they will just store it as a squashfs into the S3. And you have your image, and then what you want is to finish the configuration of your compute nodes. So you talk to boss, and then you say, I have this bunch of nodes. Just boot them, and then make sure that they have the boot with the image I want, and then finish the configuration with the recipe that I'm asking you to. This is what I'm going to do. So boss is going to talk to other different microservices and do so. So you buy the machine, you ask for CSM, this is what you got, and this is how we have been operating the system so far. So now I'm going to try to talk about the problems that VSEF, which is again the working structure, one of the working structure I work with, the problem that we saw and the problem we are trying to, the solution we are trying to provide. I forgot to mention this talk has been split, this topic has been split in 2 talks. I'm giving the first one, I'm giving a low-level overview of how things work. But then tomorrow there is another talk from Felipe Cruz, who is the working structure leader. And he's going to give you a high-level overview. So if you think that this problem is interesting to you and you want to know more about the strategy, how we got, how we dig into this problem, etc., then tomorrow should be a good talk to attend. I think it's tomorrow at 12. Okay, so go back here. So what is the problem we try to solve? So we have been running the machine, as I mentioned before, and at the same time, we're trying to be multi-tenant. So multi-tenant normally will mean, if you try to be efficient, is you want to scale the number of different clusters you have per system administrator. Now, what is the current situation? At the moment, we have a bunch of high-level sysadmins, and they have to look after the whole technical stack. They have to look after the kernel, applications, operative system, programming environments, and the software that sits on top of it. Most likely, it's going to be a workload manager. But again, if we want to be truly multi-tenant, we should be ready to run many of the things on the machine. And this adds a lot of complexity, because now suddenly the system administration are exposed to a lot of problems. Diversity of the configuration of the type of software they have to run, the variety of the software now they have to be familiar with, and it's hard to scale this model. At least this is what we think. Now you have to consider that, okay, you might have a cluster already configured, but then someone else might want to do something outside. Let's say I want to do something crazy. Let's say I want to run Kubernetes of it. So the person who is familiar with this stack might not know Kubernetes, so someone else might need to jump in. This person needs to be familiar with the full pipeline that he's going to be using, because his work is going to sit on top of it. And if there is a problem, let's say, for example, the kernel we use is the kernel provided by the vendor, so it's a specific kernel. It's not the same kernel that you will use by the people who created the solution that you are trying to deploy. Again, for example, Kubernetes, and you might have problems here. So obviously, if you are in that situation, you will go to the system administrator who deploy the system. But again, because this person is trying to manage multiple clusters and taking care of the full software stack, it might be hard to find time from them in order to help them. Okay. So what is the proposal that VSEF is trying to do? So basically we are saying, okay, so that software stack is very high. It's going to bring a lot of uncertainties, and it's going to bring a lot of problems. So why don't we break down the infrastructure, and then we divide it into roughly 2 layers. One layer is going to be the baseline. We're going to be the hardware, the kernel, the operative system, and then we will build a software layer there, which is going to be the entry point of the infrastructure that the end user is going to be running with. It's going to try to deploy. For example, you want to deploy Slurm, you want to deploy, I don't know, a GitLab runner, because you have pipelines there, and those pipelines need beefy machines because you are compiling stuff, whatever. You name it. So, okay, so how do we do this? So one approach will be like, okay, let's try to provide an interface to these users that they can operate and shape the system the way they want to shape, and they don't need to go into, let's try to avoid to people to, I don't know, for example, SSH to machine, and then give them tools that they can easier to automate. So we decided to go with HashiCorp Nomad in this case. And the reason we choose Nomad, the main reason is because Nomad allows you to run things on bare metal, but also to containerize. Now, I have to say, I haven't used Nomad to run containers, okay? So most of our focus so far has been to try and deploy a Slurm cluster using HTTP APIs provided by Nomad. Another benefit, well, another thing that we can do with this is, since we have Nomad, then we could leverage and ask the user to build the system using Terraform. We think Terraform is a friendly user technology to deploy infrastructure, and it's widely adopted. So you can use Terraform to deploy on public clouds. You can use Terraform to deploy, in this case, in Nomad. You can use Terraform to deploy on Kubernetes, etc. And then Terraform is very available out there. Actually, if I'm not mistaken, I think last year Terraform files were the most rapid repositories growing in GitHub, if I'm not mistaken. So that means that they have a lot of people using it, and there's a lot of information on internet out there in order to keep you running. Okay, I hope, I don't know about the time, hang on about the time. So Felipe is going to talk more about this slide. So basically, we are trying to break down the role of, I mentioned before, of system administrator, and then create different roles for different people. So we go from the low level of the developer who is compiling Slurm and building the artifact for Slurm, all the way up to the person who is going to be the owner of the cluster, and then is going to be taking pieces here and there, which we call vServices, and then putting them all together in a repository, and then ship it in order to give you a final impression of how your cluster should look like. Okay, so what is Nomad? Nomad is basically a job scheduler and resource scheduler. When I talk to other sysadmins, I want to introduce it as a distributed systemd, which is a HTTP interface. And as I mentioned before, one of the benefits it gives you is like you can run applications on bare metal, or also through containers. The way you interact with Nomad is you submit jobs into it. So you have a script, and through a client, you talk to the API, and then you say, this is what I want you to do, and then just run it. And the way we have been using it is to, mostly, as of today, is to have a Slurm cluster. It also gives you some sort of authorization and authentication. The reason I'm saying this is because HashiCorp, on the other side, they provide a product called Sentinel, which is more like a policy as code, if I'm not mistaken, which gives you more, it's more features that the default policies that Nomad will give you. But yeah, and then another nice thing of Nomad is the life cycle. So you submit a job, and then within the job, Nomad will give you, the job has a life cycle, so you can define what you want to do before running the job, what you want to do to run the job, and what you want to do when the job finishes. So we're trying to take advantage of this in order to having the stuff we want to have installed, then run it, and when the job finishes, we're trying the best we can in order to clean the file system. So this is a tricky thing to do. If we are successful, then we could potentially leave the node clean after the job finish. And that means hopefully we won't be able to reboot machines. So, okay, so Nomad has different abstractions that it works with. The most generic one is you deploy regions, and the easiest way to see a region is a single set of Nomad servers. So Nomad is a distributed application, have what they call agents, and the agents can have two roles. One role is the server, the other role is the client. The server orchestrates the clients. They have an overview of the hardware, the nodes they have, etc. And then the clients will just, the workhorse, they just run the applications. Now within a region, you have data centers. We are currently using data centers as a synonym of tenants. And within the data centers you set up different clients. And we put one client per physical machine. Now, another concept is the namespaces. So namespaces doesn't have the same meaning as you would call in Kubernetes. Namespaces is basically just a logical group of jobs. Like in our case, we could create namespaces. We are currently creating We currently don't have a clear differentiation between namespaces and data centers, but to give you an example, you could use namespaces for Slurm, to run Slurm applications, etc. So quickly, I have 30 slides, and I'm in the 13, so I'm going to be very quickly now. So you can encrypt the communication, same thing as Kubernetes. You have 3 certificates, the CA, the private, and the public. And they're configuring them. We have policies. In the policies, we define what the user can do. So, for example, we define policies on the namespace level. And on this one, this is a policy for administrators, so the guy can do whatever they want to on the namespace, meaning they can deploy jobs, kill them, etc. Okay, so this is a job. So now, I'm going to just give you a few hints of how to create a Nomad job. So here you define a type system, which means you want the job to run on all the compute nodes, the priority, namespace, and the data center. This is the lifecycle pre-start. This is how we define how we want to deploy the application. This is how you run it. So this is the live hook when the application is running. And then when we finish, you see here that we are removing Manji. We also do more stuff. We delete configuration files, etc. But hopefully, if you follow this approach, then potentially you don't need to reboot machines, potentially. Terraform, scripting language, API-driven, very different to Ansible because Terraform needs a HTTP API to work with. HTTP provided by providers. We have providers for Nomad, Kubernetes, etc. We are now working on a Terraform provider to deploy the Slurm controllers through Kubernetes. Huge adoption, and if you don't like HashiCorp, you can go to OpenTofu, which is the open source community version. They are encapsulated. We create these services, which is an encapsulation of a Terraform script, which can be injected through another Terraform script, which will define the vCluster. Okay. So the idea is you have a user, you compile your Slurm, you put into a repository through a CI/CD pipeline, your job finished there. Then you put the hat, can be the same person or a different person, of a vService, and then you create a Terraform script which goes to a Git repository or artifact repository. You pull the binary, and then you add all these variables into a Nomad job, similar to what I showed before, which is going to be a template that Terraform is going to finish it up, and that will submit a job to Nomad, and then we'll have your application running. This is just an example. I'm going to skip this. And at the end of the day, you have the vCluster, which is another Terraform, which will inject different vServices, putting them together, and submit your job. So if you see their source, this is a Git repo to the V service, which is another Git repo with the Terraform that I mentioned earlier. And on our work, we define different variables where you can specify which part of Slam you want to deploy. Sometimes you don't want to redeploy, I don't know, Manji. You already know that Manji is in the node. You just want to reuse it, etc. This is how it looks like. vCluster owner has a Terraform and some variables to define the template. It goes to GitLab spawns a CI/CD pipeline. It will finish up the template for the Nomad, and then it will push it to Nomad. And eventually, you will have your Slam cluster running there. We have a couple of clusters already following this approach, and we are in the stage now of maturing the solution in order to make it more production ready. And at the end of the day, this is the end picture we're trying to achieve. So we reduce the workloads on the sysadmin. They should be focused on the kernel operating system and Nomad. And then different people with different expertise for the application they want to work on, they can jump in and then be able to finish the system as they want. And that's it. Challenges, security, we have to deal with security, etc. And that's it.